summation. Hess's law, okay? You learned yesterday about standard state elements and molar enthalpy information. Turns out most things I don't form carbon dioxide. Oops. I don't form carbon dioxide by burning graphite. You know, I'm forming carbon dioxide by breathing right now. It's a very complicated series of reactions that does this. That's what Hess's law says. Hess's law says I don't have to form things from their standard state elements. I can make them in a series of steps and just add up the energy changes. All right, and I'll still get the same answer. So it doesn't matter. Oops, two came up there. It doesn't matter how many steps a reaction happens in. You can always add them up to get the total amount of energy. Okay, and that's good because otherwise I could only do reactions that were started with standard state elements, and that would be a pain. I mean, it doesn't happen that way. That's not how things go. We don't make salt from adding sodium to chlorine. That's not how you're going to make it.
Why not?
Well, because it's stupid. So it's not economical. It doesn't make sense to do it that way. I'm not going to burn diamonds to fill up my fire extinguisher. Okay, pure carbon, right? Of course, diamonds aren't in their standard state, but still, I'm not going to burn graphite. All right,
That's why the economy's bad.
that's right. People were burning diamonds all over the place. All right, so let's do this reaction right here. Now, I got to tell you this. This is something that's hard to get across to some people, but I was looking through those yesterday. I told you I found some old papers when I was looking for the exact, I swear, it's the exact same reaction with the exact same equations I'm going to put on here. When people used to come back from college, I would have them give me their stuff, and it's the exact same problems on their test of one of it from Penn State. All right, it is not something you'll have to do ever again on the test. This is like a proof. If you think of it as a proof in a math class, I'm going to show you why this works. Okay, we're going to use this equation as a proof. So no, you will not have to do it. It's going to be a very long process. It's going to take you about 10 minutes just to do this one problem. All right, but on test, it's not going to. On a test, I'm going to show you at the end of this what you really can do with this. You do not need to do all this. This just shows you why it works. But like I said, it's not something. I'm not doing this for my health. I'm not doing it if you ever see it again. You will. You absolutely will. Okay. If you take chemistry, that is. Here's the deal. None of these guys are in their standard states. If I were asking you to make C2H5OH from its standard state elements, you would have had to have written C, solid, graphite, plus hydrogen, gas, plus oxygen, gas, yield. And the reason that would work, and I can get the amount of energy it takes to do it that way, is that all of these, when you look them up, are zero. They're all zero, right? The only guy that's got an energy associated with him is this. So that's how much energy it takes to make C2H5OH if you make them from your standard state elements. It will not be the same if you make them from these, because both of these guys, when you look them up, aren't zero. They have energy associated with them. So we're going to have to look at each of their individual molar enthalpy information equations, and then we'll sum them up. But we'll have to do something with them as well. Let's look at the molar enthalpy information equation for C2H4. What would that look like? Y'all agree it would look like, oops, y'all agree it would look like, oh, well, here, that's just what I said. Write that down. So we're going to look at the delta H information equations for each of these guys, because they all have some energy associated with them. So my total amount at the end is not just going to be what you look up for him. It would be if they were their standard state elements, but it's not. Okay. So I have to look up C2H4, I have to look up water, I have to look up this guy, and then do something with them. Let's watch. First of all, C2H4. Oops, why does this keep doing this twice? C2H4, we all agree that that's what the molar enthalpy. If I asked you this last night in homework, you would have done this, wouldn't you have? Right. Okay?
Absolutely.
Absolutely. You would have looked up. Now notice I didn't add them into the equation, but the fact is the delta H in the back of the book is a positive 52.3, which means if I were to put him into this equation, where would he be? He'd be on the left side, right? He's absorbing that much energy. The next guy has a negative 285 associated with him. When you make water from its standard state elements, it gives off 285 kilojoules per mole. And finally, C2H5OH from its standard state elements would look like that. Okay, now I know it's a lot to copy. I told you you don't have to do this every time. This is just your proof of why it works.
I don't think this works.
It does.
We should make him do it for homework, just because he said that.
Well, we all have homework tonight.
Oh, wonderful.
But the lab today is a pretty good one too. But it does take a while because we have some cooling down to do. And of course, always turns out this lab or the soap lab happens on one of the warmest days of the winter. The soap lab wasn't on a cold was on a cold day. If you remember that, we had cool things out the window. Remember?
Yeah.
Today, of course, it's like 50 degrees out. So
Then why are we doing this?
we have no choice. It'll still cool down. It just takes a lot longer. So we will need more than just one period. As soon as I'm done teaching this, we're going to go in the back of the lab and start it. All right. So everybody agree that's the molar enthalpy information equations for each of those guys. Now, here's a problem.
I have one question.
Yeah.
For number 3, does that say graphite?
Yeah. I just had it. That wouldn't fit on the board. It just says graphite. All right. Now here's my problem. These three equations, of the three equations, only one of them is correct. The other two are backwards. Because after all, these are molar enthalpy of formation equations. I am forming this guy. So this equation here is absolutely correct, and that value is absolutely correct. But unfortunately, I'm breaking these guys up. Now, law of conservation of matter and energy says the same amount of energy has to be associated with that process, but it's going to be exactly the opposite. This equation is completely reversed, and so is that one. This one has to get broken up, and that one has to get broken up. So I've got to reverse this equation. What do you think happens when I reverse the equation to these values? The sign changes, exactly. It's going to be the same value, but the sign is going to be different. So here's what you're going to do next. Again, you won't have to do this. Don't worry. You're only doing this as a proof. You're going to have to rewrite every equation, reversing 1 and 2. Okay, so do that right here. There's the three equations. I know it's a pain. Trust me, you won't have to do it again. But it's nice to have this in your notes. Because like I said, I style this exact same process, the exact same thing. All right, I've seen it in college tests, Penn State. Okay, you're going to see this again. It's a classic example of Hess's law. Illustrated. By the way, something neat, I also chose this reaction for another reason. Something very interesting about this at the very end. You'll see.
Yeah, sure.
Notice the values have changed. I'm saying that's not true. The values have stayed the same. The signs have changed. Except for this guy. Why did I change this guy? I didn't flip him. Right? He's the same reaction. So there's a lot to copy, I know.
Don't tell me, come on in.
All right. What am I going to do with these three equations? Well, I'm going to sum them up. It's Hess's law of heat summation, after all. All right. So let's take a look when I go to do this. Watch what happens. I want you to cross these out the same as I do. Okay. You know, you've all had algebra equations like this, where if you've got like 2x on this, if you have an equation where there's, you know, several equations, there's a 2x on this side and there's a 2x on that side, what could you do? You can cancel them out. You all know that, right? You've done that before in a math class.
Yeah.
Well, the same thing's true. Hey, any equation that works for it, including a chemical equation. Do I have carbon on both sides of this equation? Yeah, I've got 2 carbons here, right, on the right-hand side. And I've got 2 carbons here on the left-hand side. Because remember, here, let's make this in red so you can see left from right. Okay, and I'll do the crossing out in blue. You don't have to do that, but watch. So I got 2 carbons on that side. I got 2 carbons on that side. They cross out when I sum these equations up because they're going to cancel. How about hydrogens? How many hydrogens do I have on the left side? Right here, 3, right? See them? How many hydrogens do I have on the right side? 2 there. 1 more there. 3. They canceled out. Isn't that nice? How about oxygens? On the left side, I've got a half a mole of oxygen on the left. On the right side, I've got a half a mole of oxygen on the right. Got it?
Oh, wait. You have oxygen up there.
No.
You have carbons in. Yeah.
I'm just talking about pure elemental oxygen, pure elemental hydrogen. That's why these all cancel out. What's my end goal of doing this? To have the exact same reaction I started with. And the reason this works when you reverse those reactions is all of those standard state elements end up canceling out. And what is my summed reaction going to be? This guy plus this guy and yields this guy. That's all that's left, isn't it? So basically, here's what you end up with. The same thing you started with, which is exactly what we wanted to do, but now I know how much energy it takes because I've included them in my summation. Isn't that cool?
Nice.
Pretty cool. Now, obviously, I don't want to have to spend 10 minutes doing this, writing all that stuff out every single time I do a problem. In effect, what is all I have to do? If all I care about is the amount of energy associated with this reaction, and that's all I do care about, if that's all I care about, I can, now that I know that this works, what do I simply have to do to these values? Switch which ones? Well, yeah, but it's not always going to be 1 and 2. The reactants or the products? The reactants. The guys who are reacting, these two guys here, have to have their same value but opposite sign. And this guy here keeps his same value and sign, right? All right, so you know what? I can actually make an equation out of that. And here's what the equation is. Delta H of the reaction equals the delta H of the products. So the products keep their same sign. Minus the delta H of the reactants. When you look them up in the back of the book, they're going to that negative sign in front of there is going to change the sign of those guys. And that's what the equation is. Put a big box around him because that is a big equation you're going to be using all the time. Now, the point of doing all of this, by the way, going back to my goal, I mentioned probably back in the first day of this chapter. First day of this chapter, I said my goal is to come up with whether a reaction will occur or not. Turns out, if I get a negative value, that's a hint. It's one of 3 pieces of information I need that tells me whether this reaction occurs. Negative means it's what? Endo or exothermic? Exo. Okay? Exothermic means it goes from high to low energy, right? It's releasing energy. That tells me this guy is going to want to be, this part of him says, I'm going to be spontaneous. It's going to happen. Okay? If I got a positive value here, we say, well, that's an uphill battle. There are 2 other factors involved here, but as far as we know right now, this guy favors spontaneity. This particular answer, being negative, means it's going to most likely be spontaneous, everything else being equal. Of course, everything else is not always equal. We'll talk about that when we get to the next 2 things tomorrow. Well, actually one of the next 2 things tomorrow, and then there's a third thing. All right, so that's it. Let's do one problem now where I don't have to do all this crap. Calculate a delta H of the reaction for this equation. We're going to do this guy without doing all that nonsense, just using this equation right here. Just using that. And let me show you how we'll do that. Of course, you need the back of the book. You need Appendix K. All right, we have to look these guys up. Okay? There he is. I just moved them up here so I can show the work here. All right, so here's what you're going to write. You're going to write this as your work. Delta H of the reaction equals the delta H of the products minus the delta H of the reactants. Okay, I'm just going to shorten up a little bit. Delta H of the products minus delta H of reactants. Do it. Look them up in the back of the book. Look up your delta H's for each of those compounds, plug them in, and see what you get. You have to have your book with you every day, like I said. Try that, because there's a mistake people make all the time. And I want you to make it so you don't just believe me. My student teacher doesn't even bring his book today. Holding us up again.
I'm sorry, sir. Please don't fail me.
Why the hell would you ever become a chemist?
What did he say?
I said, why the hell would you ever become a chemist?
Yeah, did you know you were getting into having bulk as a student when you were...
There are things You just can't be prepared
Yeah,
for
there's
it.
things that college can't prepare you for.
Especially strength.
Now, hold on. There's a couple of things to worry about in this one. Anybody want to tell me what probably some of the things to worry about are in this? Like, for example, are those coefficients going to mean something? Yeah, you're going to have to use them. Okay, the coefficients tell you how many moles. When you look up in the back of the book, you look up the molar enthalpy information, right? So if I've got 2 moles or 3 moles, it's going to be a different value. You've got to multiply it by those. Okay, so keep that in mind. Now, I purposely want you to try this on your own because it's a mistake that half of the class in period 1 made yesterday. Probably at least some of you will do it here today, too.
Oh, there's no doubt.
All right, before you start doing the actual calculation, let's make sure you didn't make a mistake in setting it up. That's my first mistake. Take a look up here, everybody. Watch.
Yeah.
If you wrote down as your first value negative 391.2,
You're wrong.
you're wrong. You know why you did that? Because you read left to right, and you wrote this guy in there. What does the equation say? Products minus reactants. Where are my products? Here. So my first thing I'm going to write down is going to be 2 times, I should back this up a little bit.
Well, yep. I feel that.
Yeah.
You see, I told you. Your first thing is going to be 2 times the value of KCl solid. What is KCl? Value in the back of the book in Appendix K.
Negative 436.
Exactly. Negative 436.5 kilojoules per mole. All right. Now notice something about this. I'm not going to actually make you write it in there, but the fact is, you're multiplying by this 2. What does that 2 mean in an equation? 2 what?
There's 2 moles.
2 moles, right. So actually, I'm not writing it in there, but 2 moles and moles here cancel. That's why your answer comes out to be in kilojoules. You see why?
Oh, yeah.
Makes sense.
Wow, finally something basic.
Now, something else.
Yeah, really.
My next guy, who's also a product, 3 times oxygens. What's that going to be? Plus 3 times oxygen. Well, if you look up oxygen, he's in his standard state.
He's 0.
He's 0.
So it's 0.
Exactly. And then minus. Now, in this case, watch what I do here. Although it's not really important in this problem, it would be important if I had more than one reactant. And most of them, I'm going to have more than one reactant. I'm going to use brackets. Because say I have more than one guy here. I got to distribute that negative across everything in those brackets. Now, in this case, there's only one guy, so you probably won't screw it up. But still, 2 times KClO3 is negative 391.2, I think?
Yep.
Kilojoules per mole. Now, again, those brackets are there. In this case, not really necessary, but they would be if I had more than one reactant. Now, do the final thing you got to do. Add all that up, and what do you get for your answer? I don't have the final answer, so somebody, hopefully we'll get more than one person who could do the math right here.
How you do this? I never took it.
Who's got an answer for that one? Livia, what do you got? Right, she doesn't have it. Lizzie has it. What do you have?
I got negative 90.6.
Negative 90.6? Several people? Okay, sounds right. And of course, since moles canceled, that's negative 90.6 kilojoules. And that's your answer. Now, a couple things I could ask you about that, and write them down. Write these things down. Is that endo or exothermic? Exo, because it's negative. Is that going to favor spontaneity or not? Yes.
Yeah.
So it favors. Notice I said favors. In Chem 1, because I didn't want to alarm you or confuse you. I just said usually spontaneous or not usually spontaneous. That's not really accurate. It's one of the factors that favor spontaneity. We're going to learn about the other ones. This guy probably going to feel hot or cold. Is he going to release or absorb energy? He's going to release or absorb energy.
He's releasing.
He's releasing energy. Would he feel hot or cold? Hot. All right, now again, that's all dependent on what temperature it's releasing it at, if it's above or below your body temperature. But those are the generic questions I would ask you about this guy. Okay? All right, now, last thing I told you this is kind of cool at the end of these. I want to go back to that problem here a minute. You don't have to copy any of this down, just watch. Everybody got that? That all good?
Yeah.
All right, look at it. Let's go back to this equation. That's the same one we just did a minute ago. Don't have to copy this down. It is funny how we go through that whole thing and no one ever realized another way I could have written this. C2H4 plus water yields C2H5OH could also have been written about 2 months ago like this.
Oh, don't bring that back.
Wow, what? Well, you're done with organic chem.
Yeah, but we're not done with organic chem. That's an organic chem reaction.
No,
Yes, it is.
No, it's not.
As a matter of fact, what else can you tell me about this reaction?
you're a liar.
This is, what's the name of this guy?
I don't know.
Ethene, right? Plus water yields, what's that?
Ethanol.
Ethanol, the same ethanol we made in our fermentation. So ethene gives you ethanol. Let me ask you this. What mechanism does that go by?
Nobody knows.
Yes, you do.
Like how-
Think back to organic. By the way, our here it is. If you want to see it, our midterm.
Oh, come
Mhm.
on.
Here, it's on the thing there. I'm not worried about it being on there because I'm going to tell you something that, well, I should probably turn off the camera. No, it's not true. I actually, this midterm is going to be, I told you the second half was going to be open notebook. So was the first half. I'm going to give you let you use your books for this.
Yes.
So it doesn't matter if you can see those. You're going to see them and be able to use your books on them anyway. So let me ask you about this.
Oh, we didn't have a book the first half.
I'm in your notes here.
Oh.
All right, look at what mechanism would this go by? Now, you should comment that. We only learned about really 3 mechanisms. SN1 and SN2 were kind of nucleophilic substitution, electrophilic addition, and free radical halogenation. Now, which one do you think this is? What's that?
Something addition.
Yeah, what was the first word?
Electrophilic.
Electrophilic addition. Exactly. EA or electrophilic addition. How about that? And the whole time you were doing that, you never had in your head. Now, you look at all we could do with that reaction. It took me, let's just go back. Let's just take a trip back in time. I better turn that video off before.